Okay, good morning, everyone. Just check your time for me. What time is it? It's time to pass, right? Okay, so today we'll be looking at faults and fault level calculations. Remember this course is very important. This topic is very important. Just sketch a transformer. Let's say I have a cable. All right, so now we are going to have a look at faults and fault levels, okay, or fault level calculations. This is very important. The essence of this course, one is that it will help us, to be able to size our switch gear. It will help us to size the circuit breaker. Remember that circuit breaker has two ratings. We'll have the nominal rating, IN, and we'll have the short circuit rating. Like you can have maybe 100 amps, example, 100 amps, 10 kA circuit breaker. That's the nominal rating, short circuit rating. All right? And also our cable, when we set our cable should be able to handle the maximum fault current without damage. And the essence of this breaker here is to protect this cable. The essence of all these breakers there is to protect, the cable feed. All these cables. All right? So, now once we are done with this, we should be able to know how we can size our breakers, the short circuit rating of a breaker, and how we can confirm if our cable will be damaged or not when there's a fault. And also, we use the fault level calculations even for protection settings. Okay, if I have CTs and then relays, now, so we use that for protection settings. So let's start with this first, faults. Okay, let's see. So just start, these are the things we are going to cover. So we are going to look at faults in power system. Then we look at what causes short circuits. Look at what are physical damage, that we can get from faults. How do we perform fault analysis? And then we look at per unit calculations, look at fault level calculation, symmetrical components, equations and network connections for various types of faults. And then we look at, fault location. Okay, we might not cover that now. And the fault current behavior of a synchronous generator. So we might not be able to cover everything now. Remember, this is what is it called? A semester work that we have to cover in a few hours. Wow, that's a serious one. What time is it? It's your time to pass, right? Okay, so let's start with the first one. Let's briefly go through this so that it will be easy. Faults, we said, is just an abnormal flow of fault current in an electric circuit due to a fault. Okay, usually a short circuit or abnormally low impedance path. And then you can group faults into two. So if I have, for instance, I have phase A, phase B, phase C. Remember that if I have this source and I have this as our load, so if the load is balanced, right, the current flowing through here and there will be the same, will be equal, but they will only be phase shifted by 120 degrees. So they will be equal and phase shifted by 120 degrees. Okay? So, and in that case, we said the currents are symmetrical. symmetrical current. All right, they are equal and phase shifted by 120. If you add them together, you will get 0. All right. Now, so if this situation is like this, I mean, this is our system, and somebody happens to hold this together. If I hold this together, now it's going to be a line to line to line fault. But the current flowing through there and there and there will still remain the same, okay? So, and then this kind of fault we said is a symmetrical fault because the current flowing through phase A, B, and C will be the same. Even if maybe the person is standing here at the ground and is holding this together. That is a line, line, line to ground fault. Then that is also a symmetrical fault. All right? Now, what about if now we have phase A, phase B, phase C, current is flowing, and someone stands on the ground and is touching only one phase conductor? So in that case, the current flowing through here and here and here will not be equal. So this is a line, just one line to ground. So we call this asymmetrical fault. So we have a lot of different kind of faults. So we can have single line to ground fault. We can have double line fault, somebody touching, holding these two together, or we can have double line to ground fault. Okay, so you can have line to fault, line to ground. So all these are what we call unsymmetrical fault. Okay, let's just put it like this better. Let's put it unsymmetrical. We can call that unsymmetrical fault. All right. So they are all unbalanced faults. But if you look at this is a balanced fault because the current flowing through here and here and here will be the same. And they will add up and flow through this guy to the ground. Then we say it's a balanced fault, which is symmetrical fault. Now, let's look at a few things that can cause faults or short circuits. The first one is the issue of aging of an insulation or insulation failure. Remember, if this is a cable, okay, and if it's a cable, between this and that, there's always an insulation, all right? So there's insulation here, insulation there, all right? So if there is a deterioration on the insulation, what can cause that deterioration? Because it's very important for us to size our cables proper. Remember, when current flows through a conductor, let's say current flows through here, there is always I squared ROT, which is heat loss. This heat can easily melt this insulation, because this, let's say this is our insulation. This is a conductor itself, current flows through here, let's say to the load and comes back. So if this insulation deteriorates, the live and neutral can touch and they can hear a spark, which is a fault. All right, so deterioration in insulation or aging of insulation, okay, that is one of the internal effects of faults. What can cause faults? Aging of insulation or insulation failure. And also, sometimes design problem. Very, very important. Design problem. So it's a serious thing. If you see, sometimes you see a switchgear exploding. Somebody will think that the problem is that the switchgear is old, but not knowing that it was not properly sized. Let's assume that I do a fault level analysis. Okay, let's say somebody use a 10 kA 80 amps circuit breaker, and when you do fault analysis, let's say the fault level here is about about 12 kA or 15 kA. Because this is improperly sized, if there's a fault here, this is going to explode. Okay? So improper, design problem is also one of the things that can cause, short circuits or faults. And also, improper installation. Improper installation, okay? Things that can cause faults. Other things, other external effects, things that can also cause faults are things like lightning surge. Okay, lightning striking on the line. You know what I mean? And overloading. Okay, so we'll just look at those things: overloading and the issue of public damage or human error. All these things can cause short circuits or faults. Okay, on our system. And then because of this, as current flows through here, there's I squared RT heat loss. If there's a short, let's say there's a short circuit, the current is going to be very high. And then you are going to have a very high current that will produce a very high thermal power. That's the power that is used to that can melt metals. Or maybe, some, what is it called? Some technicians, when they are, they want to change just a socket, instead of them to switch off from the DB board, to switch off the circuit breaker. Now, they will think that they are powerful, So you have your screwdriver, you want to change a socket, all of a sudden the screwdriver touches live and neutral. And then you hear a sound. All right, so which is not good. So we must try as much as possible to isolate our system before you can work on the system, because we don't want such high thermal power as a result of short circuit, to destroy our equipment or have a problem on the the technician. Okay, so because of that amount of fault currents, you can have a very high thermal power, and a typical higher that can be absorbed by equipment for an extended period. So such equipment is going to melt, it's going to explode. You can also have some electromechanical, like power system changing characteristics of voltages and phase balances. It can also lead to mechanical disturbance and possible damage. Also arcing and very high temperature, which can melt metals once there is a fault. Okay, so this is just an introduction. And again, now, the question now is, why do we have to analyze fault? Why do we have to do fault analysis? Fault analysis of a power system is actually required in order to provide information for selection of our switch gear, for us to select our switch gear size. You don't just say put 18 kA board or 20 kA or 25 or 10. You need to do fault analysis. Okay? And the next thing again is the essence of fault analysis is for protection settings. Protection settings. Actually, when we do fault analysis, we have what we call maximum fault level and the lowest fault level. For maximum fault level, we use that to size our switch gear, and the lowest fault level, we use that for protection settings. I'm still going to explain that later. Okay. Then another thing again, why we analyze fault is to, to check or ensure stability of our system operation. So our switch gears, they need to withstand and break the worst possible fault current. Okay, and the worst possible fault current is a solid three-phase short circuit, that is close to the switch gear. Now, what do I mean by possible fault current? Look at this. Let's say I have this source. I have this impedance of 1 ohm, and then I have this breaker, and I have my cable, let's say the cable is 10 ohms, for instance, and then I have, okay, let's say I have a load. Now, the essence of this breaker is to protect our cable, okay, whatever that is here. Now, if I have this as 10 amps, let's say 100 volts. Now, when you close this, if you close that, the current that will flow through there, through the whole of this, let me just put this 10 ohms or 9, just to make it a little bit, this cable to be 1 or 2 ohms, and this to be 8 ohms, okay? Now, current that will flow through here will be, I just want to make sure that there's no problem here. Okay, let's see, 7, 2, that is 9 and 10. All right, will be V divided by 1 plus this plus that, which is 10 amps. Do you know that with this, you can say, I need a 10 amps or 15 amps circuit breaker, just for instance. But if there is a short, let's say there's a short circuit somewhere. Let's say there's a short here. There's a short here. How much current will now flow through this short? Because this will be out. Now, current that will flow through here, I, short circuit, will be 100 divided by only this one, which in this case is about 100 amps. So this is short circuit current, and 0.1 kiloamps. So now, and this breaker should be able to open, okay, to trip without damage once there's a fault. So that means I have two ratings. This one is just for nominal operation of the entire system when there's no fault. So the breaker, all right, is rated 10 amps, anything above 10 amps trip. But if there's a short, now the breaker should even handle that amount of fault current. Okay, that is where the short circuit rating comes in. All right. So our switch gear, our circuit breaker, should be properly rated to withstand even the maximum or possible maximum fault current. So it's not just for it to withstand the full load current, but even the fault current without damage. Okay? So, and that's why we need to do fault analysis. Now, when we're talking about fault analysis, do you know what I have done here? This is actually done fault analysis, because when we talk about fault analysis, people think that, man, it's going to be something complicated to analyze fault. And there are three ways that we can use to analyze fault. Okay? Now let's start with this. So these are three methods that can be used to analyze fault. The first one is using a balanced three-phase fault, which we have to analyze it using an equivalent single phase. And number two is the use of symmetrical components. And then the third one is use of per unit quantities. Okay, so what I'm going to do is I'm going to play this video on fault analysis. Okay, and then let's see, just want to show this now. All right, so let's look at fault analysis. All right, faults in power stations, okay, or in power systems. So fault analysis. We have already seen that the essence of analyzing the faults is for us to make sure that our circuit breakers are properly sized and our protection relays, are set correctly, and also even for the stability of our system operation. Okay. Now, how do you analyze fault? There are three methods or three ways that we can use to analyze fault. The first one is just if we have a balanced three-phase fault, we can analyze that balanced three-phase fault using an equivalent single-phase circuit. Okay, so if I have phase A, phase B, phase C, now, and there's a balanced three-phase fault. What do I mean by balanced three-phase fault? Let's assume that there is symmetrical fault. I short this. You know, we can easily represent this, you know, with a single phase. So remember what I'm saying. Let's assume that I have that is a phase A, phase B, phase C, and you short this. All right, the same current that flows through here. All right, it will add up. If you go to the ground, then it becomes all this is a symmetrical fault. Even if it's grounded, it's also a symmetrical fault. All right, but now I can represent this, okay, as a single phase where I only take this only, like that. So I'll take that. If this is our source, so I'll take that only, all right, and solve. So if I have the impedance of this cable, so I'll put that there. I said, if I short this, how much current will flow? So that is the use of equivalent single-phase circuit for a three-phase balanced fault. When you have a balanced fault like that. But if you get, let's say you got unbalanced fault where you have phase A, phase B, and phase C, and you have only single line to ground fault. This is unbalanced fault. All right? So if it's unbalanced fault, we cannot use this method to solve. We now use symmetrical components. So we use symmetrical components to solve. Okay, I will explain this later. Okay, but in this case, we only use equivalent single phase. Equivalent single phase, okay, method. All right, so that's the first one, and then the second one. And then the third one is the use of per unit quantity. So we're going to look at that also. You can use per unit quantities, okay, to analyze fault. Now, let's start with the first one. I mean, the last one. Let's start with this, the use of per unit quantities. Okay, I'm just going to explain, all right? Now, what is per unit? I think I explained what per unit is when we're dealing with transformers. Now, if I have a transformer, let's, for instance, I have a transformer that is rated, and this transformer is rated Z in per unit. I mean, the impedance is in per unit, and then and it has let's say apparent power. You have the apparent power, and you have the voltage V primary, and you have the V secondary for that transformer. Now, when I said we can use per unit quantities to solve symmetrical faults, now I'm just saying that, you see this transformer, I can easily represent it like this, just with its own equivalent impedance. Okay? So if I know the voltage, so this is the voltage. Now I can easily say, okay, if I short this, if you short this, all right, how much current will flow through here? All right? And then what will be the voltage drop within this transformer when it is shorted? That is where we derived per unit quantities. Now we said, if I know the rating, the voltage rating for that transformer, right? And I have internal impedance of the transformer, which is in ohms, okay? When you refer everything to the secondary, okay? You have its own internal impedance. So if I short the terminals of the transformer, current is going to flow through this, and there's going to be a voltage drop here. So that voltage drop there will be IZ, like this. That will be the voltage drop, right? But remember that this Z is in ohms, okay? And then this current, which is your short circuit current, is like your full load current, okay? The fault current is in fact, let's call this base current. Now, what is base first before we continue? What is base? Because we'll be dealing with base values, you know. Now, when you have this transformer, okay, if you go to the nameplate of the transformer, you are going to see the apparent power of that transformer. You are going to see the voltage of the primary, the voltage of the secondary. You are even going to see the I full load. You are going to see the Z, this in per unit. So all these parameters, these ones, S, V primary, V secondary, and I full load, they are the nameplate rating. That is the nameplate rating, right? That is a base value for this transformer. So if I short this, that full load current is called base current. Okay? Now, the per unit quantity now, in this case now, means the ratio of this voltage drop with respect to the rating, the nameplate voltage rating, this base value, VB. This is what we call Z in per unit. That's what we call Z in per unit, okay? I base multiplied by Z, that is a voltage drop. If I multiply this, that's a voltage drop within the transformer when it is short-circuited. Now, divide by that. If you divide this, that is what we call Z per unit. Let's see whether what I'm saying is okay. Now, let's see. So, remember that if I have I base over V base from Ohm's law, V over I is impedance. I over V, okay, is 1 over impedance. So 1 over Z. But this Z is as a result of this base value. So I'm just going to put 1 over Z multiplied by this Z, which is in ohms. Can you see that this is the same as saying Z in ohms over Z base? This is what we call Z per unit. And what is this? It's actual impedance. So actual impedance over base impedance. So this is actual impedance over base impedance. That is what we call Z in per unit. So it means, that per unit quantities, like percentage quantities, are actual fraction quantities of a reference quantity. Okay? That is the actual quantity. The quantity we are talking about now is impedance. Actual impedance over reference impedance. The reference impedance is our base, the reference, the nameplate. Okay? So that is now what per unit is. If someone asks you, what is per unit in the very first place? No, per unit, anything in per unit just means, it means a ratio, just like means the fraction of the ratio of actual quantities to a reference quantity. Okay? Okay, ratio of actual quantity to a reference quantity. All right? So in other words, Z in per unit means Z actual over Z base. The base is the reference. I current in per unit is I actual over I base. Voltage in per unit is V actual over V base. Just like that. Okay? So, Now, and remember that if I multiply by 100, it becomes percent. So sometimes you can see the quantities given to you in percentage instead of PU, but it's the same thing. Just if I multiply by 100, so what's what you get will now be in percentage, okay? But that is a ratio that we call Z in per unit. The same thing here, I in per unit, actual V in per unit, all right? So if I have this like that, let's say Z in per unit is 0.1. Okay, remember 0.1 is the same as 10%, right? So either you write it like that, the Z to be 10%, or you write 0.1 in per unit. So 0.1 per unit is the same thing as 10%. Okay? So, now, do you know that if you got maybe impedance, that's Z impedance. Let's start from what we have done now. From here, we said Z per unit is the same thing as Z, which is in ohms, that's the actual over Z base. Now, we know that this Z base, if you just remember Ohm's law, can be written as V squared over S base. All right, so that if I have a transformer like that, and this is 11,000 volts, and here is 400 or 415 volts. The base value, the Z base for this transformer, I mean the voltage, the base voltage for this transformer on the primary is 1,000. The base voltage on the secondary is 415. So depending on where you want to get the Z base, whether you want it this side or that. Remember what we did in transformer when we try to refer all impedances to the primary or refer them to the secondary. So if you refer to the primary, whatever you get there is your Z ohms or Z equivalent 1. You can use that Z equivalent 1 to calculate the per unit impedance. Okay? So now what I'm saying now is when you have this, let's say you have a transformer like that, okay, and you refer all the impedances to, let's say, to the secondary, becomes Z equivalent 2. If I take that Z equivalent 2 and divide it by the Z base, that will give you Z per unit. And do you know that the same thing, even if I refer all impedances to this primary, I have Z equivalent 1 divided by Z base. This will be the same thing as that, which is Z in per unit. The essence of knowing this per unit value for input for transformer is for us to be able to represent this as a single value which does not change whether you refer it to primary or to secondary. Okay, please play back the videos on transformers. All right, you see what I'm talking about, referring impedances, okay? All right, so now that's by the way. So now it means that we can easily calculate Z base, what is it, by saying V base squared over S base. Okay? Even here, what will be I base also? Using Ohm's law, I base will be S base over root 3 V base. Remember that S is root 3 IV. So if I want to get I base, I'll just take S base divided by root 3 V base like that. Okay, so you can use Ohm's law, you know, for all this. All right. Now, let's look at just one question. Okay, just for clarity's sake, let's assume that you have a problem like this. Let's say you have a transformer which is rated, say 500 kVA transformer, 500 kVA transformer, and it's 11,000 slash 400 volts transformer. And then on the nameplate is rated Z per unit 0.1. And the equation is calculate Z equivalent 1 and Z equivalent 2. I know you know what I mean by Z equivalent 1. I'm saying the impedance of the transformer refers to the primary. That's the ohmic value in this case. This is per unit value. I want the ohmic value of that transformer because we said if I refer all the impedance to the transformer, it will look like this. So here, there will be nothing there. All impedances, Z equivalent 1, they are all here. So what will be the value? Z equivalent 1 for this kind of transformer. Okay? So remember that this Z equivalent 1 is in ohms. That is your actual value. Or if I refer that to the secondary, so I have Z equivalent 2. So if I short that, okay, remember? So this is Z equivalent 2. So they just want us to calculate that from this transformer. Let's see how we get it. So what we do, now this is Z per unit. Z per unit is Z actual over Z base. But this Z actual is your Z equivalent 1, right? If we're dealing with 1 now, over Z base. All right? So that means that from here, Z equivalent 1 is Z per unit by Z base. Z per unit is given to you 0.1. What is Z base? Z base from Ohm's law is V squared over S. So V base, S base. And I'm looking at Z equivalent 1, which is here on the primary. So on the primary side, what is V base? V base is what is here, 11,000. On the secondary, I mean the apparent power is 500,000. Okay? So that Z equivalent 1 will now be Z per unit, which is 0.1 times that, about 500,000. Okay? Did you get that? So you will get, let's say, how much? About 24.2. You get about 24.2 ohms. The same thing, Z equivalent to, that is on the secondary side, will be 0.1 times V squared. We are using the voltage there. Okay? That's a 400 squared. 400 squared over 500,000. Right? I think from your book, this is 440. So we just put 440 there. From your document, we have 440. All right? So that's all. So when you multiply out, you will get 0.039. 0.039. All right? Did you get that? Okay. So remember, we are going to use this when we start when we start the fourth analysis. Okay. Just to give a brief overview of this concept so that we can use it effectively. All right? So, now the next thing again we are going to look at is if I have this kind of transformer and then maybe from Actom and then I join this and this transformer is going to be integrated to, okay, going to get a supply from another transformer of, let's say, 132 kV is to 11 kV. And that is, let's say, it's a 1 MVA transformer. And the impedance is, let's say, 0.22, okay, in per unit. and the Z in per unit is 0.22. Now, when you have something like this, remember from what I have solved here, this particular impedance, this one being Z in per unit, means that I can even represent this as an impedance like that and say Z in per unit 0.1. So if I want to link this to this other transformer with its own impedance as 0.22, like that, to solve any problem, for me to solve problem with this, now I need to ask myself, what does this 0.22 means for this? And what does this 0.1 means for that? Remember that with this 0.1 means the impedance in the transformer when it is shorted. And when it is shorted, the rating of this transformer is different from this. So this 0.1 is based on 500 kVA. Okay, that voltage drop. Okay, but here, this is based on 1 MVA. And if I'm going to solve this, they have different bases. This is based on 500. This is based on 1 MVA. So I cannot leave them like that. So I need to give them a common base. I'll tell maybe the manufacturer, I'm just saying for example, not that you tell manufacturer like that, I'll tell manufacturer, okay, oh, your Z per unit be 0.5 for 500 kVA. What about if I ask you to provide a 1 MVA transformer with this configuration? What will be the Z per unit? Okay, so now we need to in other words, we need to convert this to a new base. All right, so let's get that conversion. So we're looking at conversion from one base to another. All right, conversion from one base to another. So in per unit calculations, the apparent power must be the same. We have to make them to be the same. Just like when we are dealing with a single phase, when we have loads, we should have a common voltage. So that we'll say V equals to IZ, and I is V over Z. When you are dealing with per unit, you make sure that all the impedances, they are of the same apparent power. Okay? So that is now when we look at conversion. So this one is based on this, but this is based on that, so that they are not based on the same apparent power. So we must choose a common base. So choose a common base. Let's just get a common base for both transformers. Okay? Now, so if, for instance, I said I have this, let's assume that I choose 1 MVA. Let me take 1 MVA. So I will say, okay, wow, this Z per unit, this 0.1 for this transformer is based on 500 kVA. It's based on 500 kVA. All right, what will it be? What will this be if I base it on 1 MVA? Okay, what will be the value? If I tell this man I want a 1 MVA transformer, so what will the value? Just go back, this is just grade 12 again, you know. This is based on that. What will be based on 1 MVA? All right, so you said is this times this over that, which is like your 1 MVA over 500. Can I just put this like 0.5 MVA? Okay, times 0.1. Remember that 500 kVA is just the same thing as 0.5 MVA. Okay, so I have 1 over that times 0.1. So what is here? It means that Z, if you want to update from one base value to another. So you say, okay, the Z per unit new, like this is now our Z per unit for this, the new one now. Z per unit new will be the same thing as, you see, I have here, this is now the base, S base, new over S base, let's say old, the old S base, that is the given S base, multiplied by Z given. So you see now, so is Z base, S base new over S base old by Z base given to you. So if I want to convert this to a new base, so I'll just say, okay, it will be this that is given to me multiplied by the S base new divided by the S base divided by this S base. Okay, so all right, did you get that? So how we got all the impedances? Okay, now we're now looking at how we can convert from one base to another, right? So now in this particular case, as it is like this, now we are going to have a look. Let's see. So if I choose base S base to be 1 MVA, now it means that the impedance of this transformer, for this transformer, T1, for T1, Z per unit will remain 0.22 pu, because I've taken this as the base for everything. And then the Z for transformer 2, Z per unit new will now be, we use that, we said it's 1 MVA over 0.5 MVA times what is given, 0.1, which will give you 0.2 in per unit. So that you can now represent these two transformers easily and solve anything that you want to solve. 0.22 and here is 0.2. Okay. All right, remember I'm just giving you background so that once we start problems, it will be easy, okay, and we can move faster. All right, so let's look at this problem. Can I clean? Okay, let's see if I have that. All right, so now let's look at this question. I think I have it here. So I'll just solve that quickly. Look at this question like this here. All right, it's a 100 MVA, 11 kV generator with its own impedance 0.3 per unit, then connected to the transformer, overhead line, transformer, and the feeder, and we have a fault there. The question is to calculate the fault current at the feeder and at the overhead line and also from the source. Okay, so now if I have that and it has its own impedance and the transformer there, overhead line, and the transformer also, then a feeder, and there's a fault here, how much fault current will flow through there? All right? We're using per unit quantities. Now, this is 100 MVA, right? It's 100 MVA, 11 kV. 11 kV. And this is Z of the generator given to you as 0.3 per unit. And this is Z of the transformer. The Z is 10%, which is 0.1 per unit. And this is 11/132 kV. And it's 500, it's a 50 MVA transformer. 50 MVA transformer. And then you have overhead line, which is in ohms. Z of the line is 40 ohms. 40 ohms. And then we have here as 132/33 kV. And the Z is 10%. And this Z feeder is 8 ohms. Wow. See? So you are asked to calculate the fault. What will be the fault current here? So now what you do is we just want to see how we can represent this like this. Look, where you have a source with its own impedance, and then we'll have a transformer, we'll have overhead line, we'll have transformer, we'll have the feeder. We are saying if you short that, how much fault current that will flow. Okay? That's what we want to do. So, and if we can get all these things in per unit, Z 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 per unit, then the voltage here will also be in per unit. So that the current we are going to calculate will be per unit. All right? So let's start now. Before, if you check here, this is 100 MVA. So the voltage drop, the percentage voltage drop based on 100 MVA is 0.3. That's the per unit value is 0.3. But this one, 10%, which is 0.1, is based on 50 MVA. This one is 40 ohms, so actual value. This per unit based on, this is also 50 MVA. Based on 50 MVA, right? All right, and this is in ohms. Wow. What do? We have to choose a common base. Let's just get any base, S base. Remember, you can choose anything. Even if it's not here, you can choose 200, 150, 100, anything, any value. You still get the same answer. Okay, but for simplicity, we'll just get one. Maybe let's get an S base of 100. Let's say 100 MVA as our S base. If it is, it means that the Z of the generator, which is 0.3, will remain 0.3 in per unit. Because now we are using the base of 100 MVA. So this will remain 0.3 in per unit. Also, not that one. That is this 0.3 in per unit for the generator. Okay. So 0.3, and then what about the transformer? So for transformer, this is already given to you in per unit, 0.1, but it's based on 50, so we must update it to a new value, which is now 100. So I'm going to say 100 Z of transformer 1 will now be 100 over 50, that is S base new over S base old, times 0.1, which will give you 0.2. Okay, so that means here is 0.2 in per unit. Then you come here also, the next one, Z of, let's just do the transformers first. Z of transformer 2 is the same thing as 100 per 50 times 0.1, which is 0.2. So Z of transformer here is also 0.2 in per unit. Okay. Then now the next is here, Z of the line, Z of overhead line. How do you get that? That value is given to you in ohms. What is that? What is ohm actual value? Remember we said Z in per unit. Z in per unit is Z in ohms, that's your actual value, over Z base. Okay? What is given to you here is in ohms, that's the actual value, not in per unit. So I need to convert to per unit, I must calculate Z base. And the Z base is V base squared over S base. So you ask yourself, what will be V base here on the overhead line? What is the rating? This is 132 kV here, 132 kV. So this is 132 on the voltage. The voltage there is 132,000 squared over S base. The base that we have chosen, 100 to the power 6. Okay? Let's get my calculator. All right, so now you just take that 132,000, then you square that, divide 100 raised to the power that will give you about 174.24. Okay, so that means that the Z in per unit will now be, we take that 80, that 40, divide by 174.24. Okay, so 40 divided by that is 0.23. So here is 0.23. Okay. Now you come here also, the feeder. On the feeder, so we do the same thing. Z per unit will be 8, how much is 8 over Z base? But Z base there is V base squared. What's the V base there? Here is the same, 33,000. 33,000 over S base. S base is 100, right? 100 times the power 6. So we have the 3 squared divide 100. 10.89. So that this becomes 8 over 10.89. 8 divided by that will give you 0.73. Okay? So here is 0.73. Right? That's all. So with that, we can easily calculate I short circuit. So we get I short circuit. Let's see if I have it. Let me just do it here because I'm going to use it for something. So I short circuit will be equal to V in per unit over Z total in per unit. Okay. Now, what is the voltage in per unit? Remember that this voltage here is in volts. Okay, not in per unit. This is in volts. Okay. So what will it be in per unit? It will be 1, because this is the actual value, and right there, the voltage is 11,000. All right, so the actual is 11, and the base is 11. So I'm going to say 11 over 11, which is 1. All right, so let's just do this here. Actual circuit will now be 1 over the total impedance. Total impedance is this plus that plus that plus that plus that. 0.3 plus 0.2 plus 0.23 plus 0.2 plus 0.73. That's the total impedance. So let's get that. So I have 0.3 plus 0.2 plus 0.23 plus 0.2 plus 0.73. So 1.66. So that is 1 over 1.66. So 1 divided by 1.66 will give you 0.6. But this 0.6 is in per unit. In per unit. The question is to calculate the fault current, which is in amperes. So this is okay. That's how much fault current will flow, but in per unit. But in amperes, it will now be I per unit is I in amperes over, that is actual value, over I base. That means I actual will now be I per unit by I base. Okay? But from Ohm's law, I base is S over, it's a three-phase, root 3 V, S base, V base. So which will give you I per unit, we've calculated 0.6 times S base, we'll have 1,000 times 10 to the power 6, divided by root 3 times V base. Now, what V base are we using? If I'm looking at the fault here, the V base, the voltage there, which is 33,000. Okay? So let's get that. So now 100 exponent 6 divide root 3 divide 3,300 over 3,000, okay, times 0.6. That will give you 1049.72, which is 1.05 kiloamps. So the circuit breaker rating there, that we are going to put here, okay, will be more than 1.05. So you go to the market and check the nearest KA rating. KA rating. The nearest KA rating is what? It's 2.5 KA. So I'm going to install a breaker rated 2.5 KA, the short circuit rating. I short circuit rating will be that. That's the rating, okay? This is how much fault current that will flow through there. This is the size of the switch gear that I'm going to use. It's a 2.5 KA circuit breaker. All right? If I want to know the nominal, I nominal for the circuit breaker, I need to know how much load is connected there. All right? So we use the load to get the nominal rating of the breaker, and we use the fault level, the fault current, to know the short circuit rating of a breaker. So as I said, when you get this breaker like that, it has the short circuit rating of 3 KA and the nominal rating of 63 amps. Okay? All right. So I was talking about KA rating. You see this switch. It's a breaker. It's like a breaker. It's a switch, but not automatic breaker. This you switch it. If you check the terminals, what we use for that terminal, the strength of that cannot be the same thing as the kind of metal that is used here, because this one is going to take more fault current, right? So it must be able to handle higher fault current of up to 3 kiloamps. All right. Now, let's look at the next. And what we have calculated here, this we have calculated. This is what we call minimum fault current. This is, and we use this for protection settings. Okay, so let's just have a look at fault levels before we come back to this. Let's look at what fault level is, and then how we can determine the fault level in per unit. And then after that, we'll come back to this. Just get this for me, this value. Let's see. Remember, if you want to calculate this, you can see that this is generator. It doesn't mean that when you want to calculate this, that you need to go and ask ESCOM to give you the single line diagram and with all the impedances so that you'll be able to check where to add up all these things and do that calculation. Let's say this is your own transformer. So you don't need to go and tell ESCOM, I need all this, you can't do that. What you do is you can even stop, let's say there's a bus bar here where you are going to connect, right, to this system. So if you check very well, you will see that if I want to calculate what the fault, if there's a fault here, all right, you can use this to calculate what will be the fault current at that point. And that fault current at that point is now your fault current that you are going to use to calculate the fault level. I'm coming to that, the fault level. So that you ask ESCOM, what is the fault level at this point? Okay? Or what is the source impedance, the whole of this impedance at that point? All right, so now what I want to do is I'm going to clean here. Let's clean here. And let's assume that there is a fault. There's a fault here. So this is for the feeder, this for the transformer. We're saying if there's a fault here. So if there's a fault there, so we'll have only this. This will go out, will be out. And the new fault current, I per unit, will now be 1 over this plus that. That 0. Did I put, I hope I added something right there. Okay. 0.3 by 0.2 plus 0.23, okay. Don't know why I put this one again here. All right, so 0.3 plus 0.2 plus 0.23. This is how much current in per unit that we are going to get there. All right. So let's just get something like that there. So I have 0.3 plus 0.2 plus 0.23. 0.3 plus 0.2 here plus 0.23 there. Okay, equals that 1 divided by that, you will get this to be 1.37 amps. Per unit. So which in what is it called? In amperes, I actual will be I per unit by I base, which is saying 1.37 times, what is the base? Base is S over root 3. What is the S? 100 times 10 power 6 over root 3 times the voltage there. The voltage here is 132,000. 132,000. Okay, so 132,000. So I have 1.37 times 100 exponent 6 divide root 3 divide 132,000. So you get 599.2. 599.2 amps. Okay, remember that because the voltage is too high here, the fault current will be down. Okay, that's why you have something like that. If I want to get maybe the fault current at this point, No, it's going to be it's going to be higher, because I'm just going to divide 1 over 0.3. 1 over 0.3 will give you the current in per unit, and then when I get the current in per unit, 1 over 0.3, I multiply it by 100 divided by root 3 times this 11 kV. Okay, you get a fault current there. All right. So now what I'm saying now is, with this is, you can have a simple circuit like this. So now this is the ESCOM bus bar we are going to connect. All right. So, and you don't really need to ask ESCOM to give you all these diagrams, all the singular diagram for everything. Just ask them, what is your fault level? What's the fault level at this point? Okay, S fault. If you can get S fault, that's all. You can still use the same thing to solve the whole of this problem without much problem. But if I close this and assume that this is infinite, the resistance is very small, the impedance here is very small, to neglect the fault level, and I'm only looking at this downstream, what I'm going to get here is what we call maximum fault level. Okay, so let me just put, just want to put something here for us before I clean all this. I calculated this to be, I short circuit here to be 1.05 kiloamps. And also, I got a short circuit current here to be 1, 2, 3. Just like 0.6 or 0.599, 0.599 kiloamps. Okay, that is what I got there, if there's a short here. All right. Now let's see, just make sure that that is correct. 0.3, just to make sure that it's okay. So I have 0.3 plus 0.2 plus 0.23. Okay, 1 divided by that is 1 point that, then times 100 exponent 6 divide root 3 divide the voltage there, 132,000. Okay. Okay, so it's okay. So 0.599. All right, so I'll just clean this because we're going to use that for something else. Now, I'm going to introduce fault level. And then before we solve problems, now, fault levels, we say fault level is the measure of the system's ability to supply fault current or to handle fault current. And in a power system, the maximum fault current or the fault level, which is in MVA, that can flow into a zero impedance. Like if I have like that, and you short this, current that will flow through here, this is zero impedance, okay? There's no impedance there, just a short. So that can flow into that zero impedance, okay? Fault is necessary to be known for you to get the size of a switch gear. You must know how much current that it can flow into this zero impedance when there's no load. So the fault level then defines the value of this, which is a symmetrical condition. So the fault level is usually expressed in MVA or sometimes in per unit. All right, so we're then going to look at how to derive fault level in per unit. Okay, so remember that under normal circumstances, when current is flowing through a system, when it is connected to a load, all right, there's going to be the apparent power for a three-phase, which is root 3 IV, where these are rated values, base value, when there is no fault. But immediately there's a fault, there's going to be I short circuit. So the only thing that we change from this equation is this will now change to I short circuit. But V base will remain the same, and root 3, and this is now what we call S fault. That's a fault level. Okay, this is fault level. And remember what we said about per unit. Per unit is actual value over base value. So if I want to get fault level in per unit, S fault in per unit, I'm just going to say S actual over S base. And what is my S actual? What's the actual power? Okay, this is, I mean, since I'm looking at fault level, so this is my actual fault level, which is root 3 I short circuit V base divided by the base value, which is the normal value when there's no fault, root 3 I base V base. So this will take out that, and this will go with that. Then you will be left with I short circuit over I base. Now, what does I short circuit over I base mean? Look, remember that S fault in per unit is S fault actual over S base. So I short circuit over I base should be the same thing as I short circuit in per unit. So that means per unit fault level is the same thing as per unit fault current. Okay, so it means that we can write this I. You remember that current I is voltage V over Z. I, this is in per unit. It's V over Z, so it must be V in per unit over Z in per unit. It must be the same thing. Okay, and what is V in per unit is 1, remember? Because the voltage there is the actual value divided by the voltage there, which is the base value. So voltage over voltage will still give you 1. So you get 1 divided by Z per unit. So can you see that this I short circuit in per unit, which is the same thing as I fault in per unit, is 1 over Z in per unit. It's the same as S actual over S base. And this S actual is our S fault level. So what I'm saying is that S fault in per unit is S fault over S base. That is S fault over S base. But we have seen that is the same thing as 1 over Z in per unit. Can you see that S fault over S base is S 1 over Z in per unit? So that if you want to calculate S fault only with respect to per unit value, impedance, you can cross multiply and get that S fault is S base over Z per unit. This is just what I want you to know, okay? Not to derive anything. Don't derive anything here. So, but this is just what I want you to know. That S fault is S base over Z in per unit. So that if I have a transformer like that, all right, and I want to know what will be the fault level here, let's assume that this is infinite bus bar, and we're asked to calculate S fault here. If I know the nameplate rating of that transformer, and I know the impedance of the transformer in per unit, right? If I know that, and I want to get the fault level here, I'll just say, oh, wow, S fault is S base over Z per unit, which is, if for instance this is 1 MVA and this is 0.22, I just say 1 MVA over 0.22. That's all. That will give you the fault level at this point, if there's no cable here. If there's a cable there, and I want to calculate S fault here, I must have this S cable in per unit, and then I have that in per unit, and I have that. So S fault here will be S base, which is that power, divided by Z of the transformer plus Z of the cable, but all in per unit. And when you do this, this is what we call maximum fault level. Okay, that is what we can use to size our switch gear. All right, it's what we use to size our switch gear. All right, so now I just want to show you something. So we said that S fault is the same thing as now S base over Z in per unit. So remember that S fault is √3 multiplied by V multiplied by I short circuit, right? And the S base is also √3 multiplied by V multiplied by I base. But this I base, as I said, the rated current. So we can just say like full load current in that case, now over Z in per unit. So if we cancel out this, now it means that I short circuit can also be written as I full load over Z in per unit. Okay, so you should know that also. You should know this. So if I have a transformer, it's a 500 kVA transformer, and let's say it's 11 kV / 415 volts. Right? If I want to get the fault level here, now, or the short circuit current, right, at this point, you can still just look for the full load. I full load is S over √3 V, which is 500,000 divided by √3 times 415. Now, whatever you get there, you can now divide that by the impedance. Let's say the impedance, let's say this is Z per unit is 0.1, just for instance. So we have 500,000 divided by √3 divide 415. You get about 695.6 amps. Okay, so if I want to get I short circuit, I'll say it's I full load over Z per unit, which is 695.65.6 over 0.1. Okay, which will give you 6956 amps. That is 6.956 kilo amps. All right, so the switch gear you are going to put here should be rated more than 6.95 kilo amps. So if I can put a 10 kA, let's say I have a breaker here to be a 10 kilo amps circuit breaker. Remember, if you want to know the rating, remember here the nominal rating or full load rating is 695. So it can be a 700 amps 10 kA switch gear or circuit breaker. Okay, so the nominal rating IN, all right, is based on the full load, and then the short circuit rating KA is based on the fault current. Okay, so either you solve this way, or you just get this first. S fault is S base over that, right? S fault is S base, which is 500 1000 divided by Z in per unit, 0.1, which will give you 500, add more 0, okay? 1, 2, 3, 4, 5, 6, about 5 MVA. So that is our S fault. So that our I short circuit will be the same thing as S fault over root 3 by voltage, which is 50, or 5 million, 5, 1, 2, 3, 1, 2, 3, divided by root 3 times 415. Okay? You can use either here like this, or you just do that. So we'll have 5, 1, 2, 3, 4, 5, 6. Now divide by root 3, divide 415. So you get 6, 9, 5. Okay? 6956 amps, which is 695.6 kA. All right, the same thing. Okay, so anywhere you can, whatever you can do, all right, you just use the same. Now, what again can we see here? I think that's all. So just know this fault level. So can you see when I get my fault level, this is about 5 MVA. So either you tell maybe ESCOM, ABB, okay, that I need more than 5 MVA switchgear, okay, or that you need a switchgear that is rated 10 kA, okay, 10 kA switchgear. All right. Okay, so let's continue the video. Thank you. So it's a maximum fault level. Did you get that? All right. So now let's come back to this system. Let's come back to this question here. Remember, if you understand these basics, then you can solve any problem, okay, on fault levels. So please note this, that S fault is S base over Z in per unit. Okay. Now, let's assume that you have a problem like this. And you have that impedance as 8 ohms. And you have ESCOM bus bar. And you are asked to calculate the fault level at this point. Calculate fault level, from there calculate the fault current. Okay. So here, this is let's say this is 132/33 kV, and it's a 50 MVA transformer, and it's 10% impedance. So look, as it is like this, you don't know what is going on here, like you don't know all these things, but you just know this and that only, and you didn't care about the fault level at the bus bar. So you can solve from here to get the fault current here by saying, okay, this is already in per unit, this one is in ohms, I need to convert this to per unit. So Z in per unit is Z in ohms over Z base. So Z base is V base squared over S base, right? Now, what is the V base here? It's 33,000 squared over, see, the base here. Now, I don't know what is going on here. You see, I'm only looking at this. So my base value for now is 50, okay? So 50 MVA. So 50 times 3 power 6. Now, we can calculate that. We'll have 33,000 squared divided by 50 MVA. We get 21.78. 21.78, okay? 21.78, that is in ohms. So as that per unit here will be 21.78. So 8 divided by that is 0.367. Now, just here, all right? So the fault level here, S fault, will now be S base over Z. But this Z is in per unit total, right? So S base is 50 divided by this Z, 0.1, plus this Z, 0.367. So 0.367 plus 0.1, then 50 divided by that will give you 106, let's say 107 MVA. So that's the fault level at that point. Okay. So now, what would be the short circuit current? I short circuit is the same thing as S fault over root 3 V. And S fault is 107 times 10 to the power 6 divided by root 3 times the voltage there. And the voltage here is 3,000. Okay, so I have 107 exponent 6 divide root 3 divide 3,000. So I have 1.87 kilo amps. So now, what I have here is 1.87 kilo amps. But if I check what I calculated from the whole of this, I got this to be 1.05. Okay, so now this is I short circuit as 1.87, and the fault level is this. So if I want to even buy a switch gear, if I want to buy a switch gear for this, I'll just tell Actom ABB that I need, let's say 110 MVA switch gear or a 2.5 kA rated switch gear. So this is what we call the maximum fault level. But if you check the fault level calculated here before with the whole of this, let's see the fault level here. It is short circuit current as fault is root 3 times the short circuit current 1050 times the voltage there is 3,000. Just want to get that fault level there. So I have root 3 times 1050 times 3,000. That is 60 MVA. 60 MVA. You see, this is small. It's about 107. This is 60. So this is a minimum fault level. But this is a maximum, or the highest fault level that we can get, assuming that this is infinite bus bar. Okay? So sometimes you need to, if I want to get minimum fault level here, I need to ask ESCOM to give me the fault level at this point. If I can get a fault level here, then I will use it with what I have here to still arrive at this minimum fault level. Okay? Sometimes, if you don't know, if they don't give you this, they can give you I short circuit, or they can give you the ZS. Any of this. So let's assume, what did we get as I short circuit? We got 0.599 Ka. All right, but you need to know at what voltage. At what voltage? The voltage here is 132 kV. You can use that short circuit current with the voltage to know the source impedance. And then use that source impedance together with all these impedances to get the fault level at this point, the new fault level, which is that. Okay, so let's just finish up this so that We'll be able to solve problems, okay? Now, remember, when you have a switch gear here, or a switch gear there, a switch gear contains bus bars. Even so, all the bus bars should be able to handle that fault level. The strength of your bus bar should be able to handle the prospective short circuit current. Okay? And then when we talk about infinite bus bar, we are saying that we are assuming that the the ZS upstream impedance is negligible, is zero, is infinitesimal. Okay? All right. Another thing again that you need to know is the rating, the short circuit rating of a cable. Can you see now that this cable here should be able to handle this amount of fault? Now, if I want to know whether this cable will damage or not, so what I need to do is you use this equation. I short circuit is Ka over root T. This is the short circuit rating of a cable, where K depends on the material, the material constant, and this is a cross-sectional area, and that is the trip time of breaker. The time it will take that breaker to the breaker here that is protecting that cable, the time it will take that to trip. For instance, let's assume that this cable is 35 mils cable, right? So the amount of current that this cable can handle without damage, let's say in 1 second, will be the K of that. If it is a PVC cable, the K value, this constant for a PVC, is 115 times the cross-sectional area, that is 35, divided by the square root of T of 1. If you do this, maybe you get about 4 kiloamps. This is how much this can handle in 1 second. And if you check how much fault current is flowing through there, it's about 1.8. So that means that this cable can handle this. I mean, if this cable is 35 square millimeter cable. Okay? Did you get that? So when you want to do fault analysis or fault calculation, the primary equation to be answered when doing things like this, first one is your switch gear suitably rated? Because if you put a wrong Ka rating of a switch gear and there's a short at the bus bar, at that board, that switch gear is going to explode. Sometimes when you see switch gears exploding, so you will think that maybe the problem is that maybe it might be that the switch gear is old. The switch gear is not old. It might be that the person that sized the switch gear, the engineer did not do a proper calculation. So the essence of fault level calculations is for us to make sure that our switch gear is properly or suitably rated to handle the prospective short circuit current. And also the next thing is to make sure that our protection scheme will be able to detect the fault. Okay? Will your protection scheme detect the fault? How do you know? You must make sure that you get your minimum fault level, the fault current. If not, you are going to have a problem. And if your protection scheme is not able to detect the fault, then it means that your equipment is going to rupture, and we don't want that. All right? Okay, did you get that? So when you are determining fault level, so we have a high and low estimate of fault level. Okay? So suitability of your switchgear rating and rupturing capacity the highest possible fault level. We use that to size our switchgear. But for protection settings, we use our lowest possible fault level value, where you can start everything to that point. Okay, so please, we should know that. I just checked the time for me. Wow, what time is it now? It's time to pass. Yo, it's a serious time, eh? Okay. So now, now what we are going to do, let's now see when you now have two transformers in parallel. Let's look at that scenario. If you get two transformers in parallel, all right. Now let's see. Okay, let's just. So if I have this transformer like that, and it's connected to this bus bar, and I have another transformer again to that bus bar. So, what will be the fault level at this bus bar? If I have apparent power, and then I have its own Z, apparent power and its own Z. So remember that if this is not there, let's say this is just on its own, and this is like that, the fault level here, let me just use something, let's say this is a 50 MVA, and 0.1 per unit. Now, S fault here will be 50 MVA over 0.1. So which will give you 500. This is 500 MVA, fault level. Okay? So now, let's assume that you got your board, and it's a 500 MVA board. Okay? Switch gear. Then, which you can also calculate if you know the voltage. Let's assume that the voltage is 132. 132 slash 3 kV. So if I want to get a short circuit current, I'll just say I short circuit is S fault over root 3 by voltage, which is our S fault is 500 MVA over root 3 times the voltage there, and the voltage there is 3,000. Look at I'm looking at fault level at this point, okay? Now, so if I have that, so you get 500 exponent 6 divided by root 3 divided by 3,000. So you get this to be 8747 amps. That is 8.747 kilo amps. That's the fault current. Remember, that's the fault current that will be here. I mean, if I assume this is infinite, I'm just looking at that. It's 132/33 kV. Now you get about that. It means that the switch gear that I must put here must be a 10 kA switch gear. 10 kA. You know this one, you see this one that I got about 1.0. Remember I used a line of 8 ohms, high impedance, that was able to reduce the current to about that. But if you want to get the fault level at this point, maximum fault level about 8. So here I need a 10 kA board. So I'll tell ESCOM, ABB, that I want a 10 kA board at 33 kV. Now, remember that this is feeding load, certain load. This board is feeding a load. And that load, this is 50 MVA. Let's say the load is about 40 MVA load, or 40 megawatt load, right? 40 megawatt load being fed by 50 MVA is okay. There's no problem. Now, your load now increased, let's say to to 80. Your load increased to 80 MVA. Now you say, wow, 80 MVA, this cannot take care of 80 because this is 50 MVA. My load is now about, let's say, 80 megawatt. So the load is now more than the transformer rating. What do? You bring another transformer in parallel. So let's say you bring this one in parallel, you connect it together like that, and it's still a 10 kA board. All right, let's see what will happen. Because we don't want engineers, that we just come and do something like this and create problems for us. Okay. So now what will happen? We say, okay, we are going to find a new fault level, because now once you put this and this now in parallel to feed the new load, now the fault level is going to increase. What do I mean? If you remember, when you have a source like this, let's do like that, and you have an impedance, for instance, and let's say this is 12 volts and this is 2 ohms. How much current will flow through here? I will be 12 over 2, which is 6 amps. What about if I take another resistor like that and put in parallel? About another 2 ohms. How much will now flow? So if you check this parallel, this is 2 times 2 over 2 plus 2, which equal to 1. So the effective resistance in this case will be 1. That means that new I will be 12 over 1, which is what? 12 amps, which is twice of this. Right? So if it's short circuit, the new short circuit current is twice now. So that means when you have transformers in parallel like this, the fault level at the board is going to double. Wow. So that fault level that we calculated, the fault current we calculated, is going to be twice. All right. So now the new fault current will be 8.745 times 2, which is about 17. And this board is still 10 kA. Now it's 17. That is the fault level at this point, or fault current at that point. But the board did not change. So if there is any fault within the board for this installation, this board is going to explode. And this is one of the problems that we're having when people parallel transformers and they don't know this. That's why we talk about upgrade. Don't just say, I'm adding a new transformer. No, I'm upgrading the system. Because once you put a new transformer in parallel with this, then you must recalculate to make sure that the cables, the switch gear, the bus bars, everything that they are able to handle the new increase. Okay, the increase in fault level. All right, so when transformers are in parallel, the fault level is going to double. Did you get that? So it means we can just write it like this, the way it is. I think I put it here. Just like this. Okay, that for n transformers in parallel, the new fault level at the secondary terminal of that transformer will be n times the fault level of one transformer. So you have 2 transformers in parallel, the fault level will double. If you have 3, it will triple. Okay, did you get that? All right. So now what again do you need to know? Because you need to know some of these terms, basic terms. Now, if you check, let's say I have this impedance, and I have voltage, and I short this. If you get any short circuit, which is your voltage divided by Z Total, but this voltage is a single phase in this case. Okay, like this. Divided by Z, right? So that is your I short circuit. And also, if I take this and multiply by √3 for a three-phase voltage times voltage, then I will get the fourth level. For a three-phase, √3 V I short circuit, I will get fourth level. Right? So if I have a transformer, let's say I got a transformer like that, and I know the fourth level at this point. Do you know that you can still calculate, you can see even with the fourth level, go back to the transformer impedance in ohms? Because if I have this as S base, and I have this as Z in per unit for the transformer, and we say that S fault is the same thing as S base over Z in per unit, right? And we said here that Z in per unit is the same thing as Z in per unit is the same thing as V base squared over S base, right? So now, sorry, let's say Z base, you know that Z base is V base squared over S base, right? And then what again can I put in? Okay, I have S fault is S base divided by Z per unit. And Z per unit is Z in ohms over Z base, like this. All right, so I can take this and put there. So if I'm able to calculate my fourth level, and I know that this is this, so I can take this there. So let's put it there. Let's put this here. So this is S fault is S base over Z in ohms over Z base, which is the same thing as saying S base over Z in ohms by Z base, like this. Can you see that? S fault is S base over Z in ohms by Z base. But what is Z base? Z base, we put Z base there, V base squared over S base. So that means that S fault is the same as saying S base over Z in ohms by V base squared over S base. So that this can cancel out that. So you still have that S fault is the same as saying V base squared over Z in ohms. Okay. Look, I'll clean that. So S fault is V base squared over Z in ohms. So that if I want to get the impedance of the transformer in ohms, if I know the fourth level, I'll just take V base squared over S fault. That will give you the transformer impedance in ohms. If I get V base squared over S fault, it will give you your Z in ohms. Why do we need to convert per unit impedance of the transformer to ohms? Because there are two ways that we can use to analyze fault. Either we analyze them in per unit quantity, or we analyze them using the normal thing that we know from grade 12, the single phase method. That when you have a transformer with this impedance, if this impedance is given to you, Z in per unit, and this in ohms, for instance, you know you can solve this in two ways. You can just take this as it is, Z and Z, convert this in per unit, convert this one to per unit, and have the voltage like that, and solve, but this voltage will be in per unit. So that the I you are going to get will be I in per unit. Or you can have this like this, and have this in ohms and that in ohms, and have your voltage not in per unit now because we're dealing with ohms, and calculate. And your I short circuit will now be this voltage. This is now a single phase representation of a three-phase, a symmetrical fault. One is a symmetrical fault. So this is that voltage, line voltage for three-phase, divided by root 3. Now divide by Z of the transformer in ohms plus Z of that cable in ohms. See, this is the one that we know very well. So if I can get the impedance of the transformer in ohms, good. Then I will leave this one in ohms and then use this and solve to get I short circuit. Or I put this one in per unit and convert it to per unit and solve, and we'll get I in per unit, which will be 1 over Z of transformer in per unit plus Z of the cable in per unit. Remember here now there's no root 3 here. This is just 1 over something. But here is V over root 3 to get a single phase value of such a three-phase system, and divide by that. So that here, if you are given like this, you use this method that Z is V squared over S, which is S fault, for you to get the Z ohms for that transformer. So you use this to convert, if you know the fault level at that point already, you use that to convert that to ohms, and then put it here. Okay, did you get that? When we solve problems, you understand more. Okay. What time is it? What time is it now? You can see it's time to pass, right? Yo. It's time to pass. There's no time here. The only time left is time to pass. Let's see whether we'll be able to get these things right. I think the best is to solve maybe one of the past questions. Let's look at one past question. All right. So let's look at one past question. I'll just solve one question and then we'll be done with this for now. Okay. So let's look at this question. Slide 51. So that is on slide 51 from your study material. Slide 51. Let's look at this question. Okay. Now, did you see that question? So we have a source, we have a bus bar here. Let's say it's infinite bus bar, and then we have a transformer, and we have a line, and we have a switchboard. And this one is feeding another board. Feeding a transformer. And then feeding a bus bar. This board. Okay, it's a 5 MVA. Here is 5 MVA that's 3/6.6 kV, 3/6.6 kV, and then we have 4.6%, 4.6%, and then the cable, 70-meter cable, 70-meter cable, and R is 0.149, 0.149 ohms per kilometer, and X is 0.094, 0.094 ohms per kilometer, and that's all. And then we have also another cable here, which is 800 meters, and we have R is 0.19 ohms per kilometer, and X, okay, I made a mistake there, X is 0.094 ohms per kilometer. Okay, let's check this. 0.19, 0.094, okay, another one is 0.126, this is 0.126, and 0.149, all right? So, once again, transformer 25 kVA, 25 kVA transformer, and the 6,600 slash 550 volts. Okay, X is 3.8%. All right, so now we have this question. The question says we must calculate the fault level and the fault current at the 550 dB board. This is a dB board. It's a 550 volts dB board. So we must calculate the S fault and the I short circuit. Okay, so as I said, we have two ways of doing it. All right, we can have all these impedances in per unit, or we can have them all in ohms. Okay, so what we do is let's calculate the impedances, and then we can now get our fault level. Okay, let's get our impedances and then we'll put them to a common base. All right? Did you get that? So we choose a common base, and then we can update all the impedances. Let's see, Z impedance. Let's look at the cable. Let's just check the cables first. This is cable 1. This is Z of cable 1 is 0.149 ohms per kilometer, plus X plus J 0.126. This is in ohms per kilometer. So therefore I'm going to multiply this by the kilometer. Kilometer here is 70 meters. 70 meters 0.07. That's the first cable. That's the impedance of that cable. That is 0.149. So remember, this is one of the past questions. All right. So 0.149 plus 0.149 plus 0.126 AI equals that, then times 0.07. So I'll have 0.01366 with an angle of 40.2. Z cable 2 is 0.19 plus J 0.094. Okay. Now ohms per kilometer, so multiply by 0.8 kilometers. All right. I hope you know why I'm putting J here. This is reactance, X. And since we are dealing now with reactances and resistances, this X, you must put J. Even on the transformers, you must put J when you are solving, because they did not put Z here. This is not Z, it's X. So X, which is reactance, so you must put J there. Except if you don't believe in J. Okay, but it's live. So 0.19 plus 0.094. 0.94 J equals that times 0.8 equals that. So this will give you 0.17 with an angle of 26.32. Okay, so this is the Z impedance. I mean the impedance of the cable. Now, this is in ohms, all this is in ohms, but this is per unit and not in per unit. So we must get everything first in per unit, right? Because if I can get everything in per unit, I'm just going to have transformer impedance in per unit, cable impedance in per unit, another cable in per unit, and this transformer in per unit. That's all. So if I can get Z of the transformer 1 plus that Z of the cable 1, Z of cable 2, and Z of the transformer 2. If they are all in per unit, then I can easily calculate I short circuit. All right? So I short circuit will be in per unit, which is 1 over Z total in per unit. So let's just get those Z's. So choose a common base. Let's choose a common S base, because this is based on 5 MVA, this impedance. This one is based on 25 kVA, all right? And these are in ohms, so I must have a common S base. So you can choose anything. I can just take 5 MVA as our common base. If I do that, it means that the Z of transformer 1 will remain, as I said, this is reactance. So I will put J for this is percent, 0.04. But this is percent, so put it in per unit, 0.04. Now, so this will remain like that. So no problem there. Now, the next is even Z of transformer 2. Let's see what Z of transformer 2 will be. This 0.038, this is based on 25 kVA. What about if you update it to 5 MVA? So it will be 5 MVA, all right, over, this is 25 kVA, which is like 0.025 MVA, 0.025 MVA, times the impedance there, 0.038. Okay, so we have 5 divided 0.025 times 0.038. So you get 7.6. Okay, in per unit. And this is Z X. I just put X, it's not just X. So I put J there. J 7.6. Okay. Now I got that. Now let me convert this to per unit. Z base for cables is V base over V base squared over S. So the voltage, the base voltage there is 6,600. So 6.6 kV squared divided by S base. And S base I'm using is 5 MVA. Okay, so you have 6.6 squared divide 5, you get 8.712. 8.712. All right. So now if you got that, then we can easily calculate the impedance of this cable, Z cable 1. So you get a Z cable 1 will now be actual over base, 0.01366, an angle of 40.2 over that base, 8.712. So we have 0.01 0.01366 divided by 8.712. So you get 0.00157 with angle of 40.2, and then Z cable 2 will be 0.17 with an angle of 26.32 divided by 8.712. So half 0.17 divided by 8.712. That gives you 0.0195, an angle of 26.32. All right, so we got all the impedances. All right, so we're just going to let's put all the impedances, the Z of transformer 1, or the X of transformer 1. We got that to be J0.04, and the Z of cable 1, we got that to be 0.00157 with an angle of 40.2. All these are per unit. Now the next cable is 0.0195 with an angle of 26.32. And then we'll come here, transformer 2, we got that to be J7.6 in per unit. Okay, so we add them up. So that total impedance in per unit will be 0.04 I plus 0.00157 with an angle of 40.2 plus 0.0195 with an angle of 26.32, now plus 7.6 I equals that. So we get Z total to be 7.665 with angle of 89.86. Okay, so that I in per unit will be the same thing as what is it now? I in per unit will be 1 over 7.65. That is 1 over V over Z. 7.65 with an angle of 89.86. Okay. So you have 1 divided by that will give you 0.1307 with an angle of minus 89.86. Now this is in per unit, so you must convert it to amperes. All right, so you convert to amperes. I per unit is I in amperes over I base, okay, which means that I in amperes is I per unit by I base, which is I per unit is this 0.1307 times the base. I base is S over root 3 divided by the voltage. Okay? S base over root 3 and by the voltage, the base voltage there. So you just need to check what's our S base. We chose S base to be 5 MVA. What's the voltage there? You look at the voltage where the board is. The voltage at the board is 550. All right. So just to check where I can finalize. Can I do it here? Because here you got that. So that I in amperes will now be 0.1307 times 100, or is it 105 times 5 MVA over root 3 times the voltage there, where you are talking about the board there at 550. All right. So 0.1307 times 5 exponent 6 divide root 3 divide 550. Okay, so you get 686 amps. That's 0.686 kilo amps. All right. So that will be the answer to that question. Okay, what time is it? It's time to pass. Okay, so let's look at the question. It says the estimated short circuit level at the bus bar of a gen station, let's say this is a generating station, gen 1, and that's a bus bar. I'll have another generator, gen 2. Now, it says that the fourth level is 1000 MVA. This is 1000 MVA, and this side is 660 MVA. Okay, so let's look at the question again, just to All right, so the question says that the estimated short circuit VA at the bus of a generating station is 1000 MVA and the other station is 660 MVA. Then the generated voltage is 11 kV. V is 11 kV for each. And then calculate a possible short circuit VA at each station when they are interlinked with an interconnector cable with a reactance of 0.4 ohms. All right, so now, we'll have this. If you get a fault level at this point, you get about 1000 MVA. And this gen station also, if you get a fault level at this point, you get about 660 MVA. Now, if you interconnect this with an interconnector of reactance 0.4 ohms, the question is, what will be the fault level at this bus bar? Remember, without this, the fault level here is 1000, the fault level here is 660. When you interconnect both of them, the fault level is going to increase. All right? Now, we just put this maybe to limit it, but what will be the fault level here and what will be the fault level there? The increase in fault level on both sides. And this 14 marks is minus 2006. Okay? How do you do that? Now, remember, this is just if I can get the impedance of that generator, okay, X generator 1, and then I have this impedance of this, of the interconnector, and I have the impedance of that, X generator 2, and then this is reference. Now what we are saying is if there is a fault at this point, this bus bar, so here, what will be the fault level? Okay, later you also we say, okay, what about if there's a fault here? What will be the fault level? Okay, so you see everything is in order. We can use per unit method or ohmic method to solve that problem. All right, so how do we get this? I need to get this in per unit, get it in per unit, get this in per unit. Okay, so for me to do that, let's just look for base value, S base, just choose any base. Let's assume that S base, can just choose anything, S base, let's say to be 1000 MVA. All right, I need to get the impedance of this generator. If S base is this, we know that S fault, we said, is S base over Z in per unit. Remember, S fault is S base over Z in per unit. So if I take S base to be 100 MVA, and I have S fault as this, because remember this is S fault, okay? S fault 1, this is S fault 2. So now, so if I have this as 100, 1000 MVA equals that 1000, all right? What will be this? So that means that Z in per unit for the generator 1 is 1 ohm. So I have here to be 1 ohm. Okay? And then it's okay. What will be this one? You come here, you check, we said S fault is S base over Z in per unit. This is the fault level at that point. Okay, and this is our S base. So if I have 660, I would say it's the same thing as S base 1000 divided by Z in per unit. Okay, this is our fault level there as fault, and this is our base that we have chosen. So you can now take that Z in per unit is 1000 divided by 660. So we have 1000 divided 660. 1.515. 1.515. All right. So this is the impedance of this in per unit. 1.515. Okay. Did you get that? Let's see. S fault is S base over that. 660 is S base, which is 1000 MVA divided by Z in per unit. Okay. So did you get that? All right. I hope there's no confusion there. Just to explain once more, by giving fourth level at this point to be that, by giving fourth level at this point to be this. Okay. So what I'm saying, if I want to calculate their respective impedances, so the impedance, remember that I said S fault is S base over Z in per unit. So now for the fourth level of 1000, it will be 1000 equals to the base, and the base there is 1000, then over that. So for this to be this must be 1. So Z per unit for that gen 1 is 1. And then we come to this side. We are given S fourth level to be 660. So that means 660, we said is S base over Z per unit. And what is our S base? Is 1000 divided by that. So to get Z in per unit, you take this divided by that to give you Z in per unit, which is 1.515. Okay? All right, so now we got that. What about this one? Wow, this is just given to us in ohms. So we must convert that to per unit. How do we get to per unit? Well, Z in per unit or X in per unit, anyone we want to use, X in per unit is X in ohms over Z base. Okay, what's our Z base? Z base is V base squared over S base. V base squared over X base. What's our V base? Is the rated voltage, which is 11,000 squared. Also our S base, we have chosen S base to be 1,000 power 6. Okay, so let's get that value. We have, I know that if I square that 1,000 to give you 10 to the power 3, so just like 11 squared over divided by 1,000. So 11 squared divided 1,000, 0.121. 0.121. Okay, so that means that X in per unit is, we'll have 0.4 over 0.121. So 0.4 divide 0.121, that is 3.3, 3.31 in per unit. Just do it again. 0.4 divide 0.121, that's 3.31 in per unit, okay? So here is 3.31. So that's all. So if I now want to get, because the question is to calculate the possible short circuit VA at each station. The possible short circuit VA at this station 1, let's say at station 1, okay, the short circuit voltage, the short circuit level at that station will be, current will flow, when there's a fault here, current will flow from here to feed the fault, and that to feed the fault. So the whole of this and this will be in series, and this series will parallel with that. So it's going to be like that. Right, so that is where our fault is. So in other words, I'm going to have 1 ohm here. Sorry, I say 1 ohm. 1 per unit, right? Not 1 ohm. sorry, 1 per unit. Now this is in per unit. So 1 in per unit, and then here is 1.515 per unit, and here is 3.31 per unit. So that means X per unit total will be this plus that parallel that. 1.151 plus 3.31, okay, parallel 1. All right, so let's just add these are in series, so just add them together. That is 1.515 plus 3.31, okay, that is 4.825 parallel 1. All right, how do you parallel? I hope you still remember how to parallel. Just say 4.825 times 1 over 4.825 plus 1. Okay? That's when you do 1 over x1 plus 1 over x2 equals to 1 over x total, right? So we know this and that as this and this, okay? So you can solve. So we have 4.825. Now divide by this plus this is 5.825. Sorry, 4.825, 4.85. All right, so we have 4.825 divide 5.825. That will give you 0.828. All right, in per unit. So that if I want to get a S fault, we said it's S base over Z total. Now S base that we have chosen is 1000 MVA divided by 0.828. So we have 1000 divided by that, we give you 1207.25 MVA. This will be the fourth level. Have you seen, just interconnecting this and that increased the fourth level of this to 1207. But if you remove this, you'll be 1000. So if this was not properly sized, then there's going to be a problem. Okay? Once we interconnect this. So let's look at the next one. What about this point? Okay, so at station 2, so you clean this, you say if the fault is now here, this will be in series, and this series will parallel that, right? So Z total will be this series that is 1 plus 3.31 parallel 1.515. Okay, which is this plus that gives you this, and that is 4.31, okay, parallel 1.515. What does that mean? It means 4.31 times 1.515 over 4.31 plus 1.515. Okay, did you get that? What time is it? Wow, it's time to pass, right? Okay, so now let's see. 4.31 plus 1.515 equals that. Okay, now the whole of this divided by that. Let's say 4.31 So you get 1.12, 1.121, 1.121. Let's see what happens there. Now, S fault at number 2 bus bar will now be S base over Z total, and our S base is 6. S base is 1,000 MVA over 1.121. So we have 1,000 divided by that, we give you 892.08 MVA. Did you see that? The rating of this, the fault level at this point, will now increase to 892.08. Do you know the implication of this? Because sometimes, people will just say, "Look, let's parallel this together." Another person will say, "No, if you parallel together, there will be an increase in fault level," which is okay, which is true. Now they just put a reactor to limit the fault level, and they did not calculate the exact size of a reactor that we use to limit that fault level. Because this must be, for you to limit this fault level to be very small, okay, now you need to increase this size. Remember that what we have calculated here, you can convert them to Ka, but these are the two answers that they want, and that is 14 marks. If you want to know their values in kiloamps, it will be that I short circuit for the first one is S fault 1 over root 3 and voltage. And what's the S fault? We got 1207.25 times 10 to the power 6 divided by root 3 times 11,000. Here, let's just see how much that fault current will be. 1207.25 exponent 6 divide root 3 divide 11,000. Get about 63.4 kiloamps. That's how much fault current that will be here. How much fault current that we're going to get here? 63. The same thing that I short circuit 2. Now it will be 892.08 times 10 to the power 6 divided by root 3 times 11,000. So we have 892.08 exponent 6 divide root 3 divide 11,000. Get 46.8 kiloamps, 46.8 kiloamps. So now let's just see why do we need to know these things? Remember, this is the answer, right? Because we just want to calculate to calculate the short circuit VA at each station. This one and that one, okay? But I was just saying, for to convert them to kiloamps, the short circuit current, you have this and that. What does this tell you? Look at it. If you check here, the fault level, if this was not there, the fault level, the fault current will be, I short circuit here, supposed to be 1,000 times 10 to the power 6 over root 3 by 11,000. Let me just check what that is, so that you see when you interconnect what happens. 1,000 exponent 6 divide root 3 divide 11,000. You get about 52.5 kiloamps. Now let's assume that this was not there, and this guy did a design and did his calculation, And then from his calculation, he got 52.5 kA and he put a 60 kA board. All right, which is okay. 60 kA board is okay for this installation. And now, we now interconnect this with that. Wow. The fault current now increased to 63. And the guy did not change the switch gear. He just interconnect that and say, wow, everything is fine. Look at now the new change in fault current. So if there's any fault here at this board, this is what will appear there, but this board is rated, let's say, 60 kiloamps. So this board is going to explode. Okay, did you get that? All right, let's look at another question. Okay, so let's have a look at that question. It's a three-phase. It's a three-phase 15,500 kilowatt generator feeds a 5,500 kVA step-down transformer through a line of 5 kilometers long. Just want to write it out. 15,500 kilowatt generator and feeds 5,500 kVA, 5,500 kVA transformer through a 5-kilometer length. Find a rupturing capacity required for the high voltage and low voltage switches of the transformer if the power factor is 1. Okay. If I'm going to put a switch gear here, what will be the fault level at this point? And if I'm going to put a switch gear here, what will be the fault level at this point? So the high voltage and the low voltage side. Okay, the gen reactance, let's see. Let's just put the parameters. Gen reactance is 10% and resistance, let's say 10%. Resistance is 1%. And then transfer reactance, X, is 8%. And resistance is 1%. And then the line conductor, 0.5 ohms. And resistance is 0.67 ohms per kilometer. So reactance, 0.5 ohms per kilometer. Resistance, 0.67 ohms per kilometer. Okay, and then the line voltage is 20,500. 20,500. 20,500 volts. Okay, so let's look at it together. And this is November 2005. I think it's mines. Now, this is what is given. All right, the impedance of the generator, that of, and all this is in percentage. As in percentage, this one is in ohms, and then in per kilometer. Now we are asked to calculate to find the rupturing capacities for the high voltage and low voltage switches. For this switch 1, for 1 and 2. Right, so let's start. So let's look at this. For the first one, we have this generator and we have impedance, and we want to know what will be the rupturing capacity of this circuit breaker, switch gear. And the 15,500 is the size. This is 15,500. So for a power factor of 1, so it's going to be 15,500 kVA, right? Power factor of 1, we are giving power factor of 1. So the apparent power will be the same thing as the active power. Okay, and then Z in per unit for that generator will be, this is 0.1 squared plus this 0.01 squared, the square root. I hope it's okay, right? This 0.1, that 0.01. Let's just get what that is. So we have 0.1 squared plus 0.01 squared. Okay, then the square root of that, the square root of that will give you 0.1. 1 in per unit. Okay, it gives 0.00. Let's just put 0.1005 like that in per unit. Okay. Now, the impedance of the transformer, of this feeder, the cable here, this is given to you in ohms, so we must convert to per unit. So first of all, this is in ohms per kilometer. I'll have this as 5 kilometers. So the impedance first will be the square root of 0.5 squared plus 0.67 squared. This will be in ohms per kilometer. So I multiply by 5 kilometers. So let's see, we have 0.5 squared plus 0.67 squared. You get something, and then the square root of that will give you 0.836. Then multiply by 5 times 5, you get 4.18. 4.18, but this is in ohms. Okay, so you just need to convert this to per unit. So as Z in per unit will be Z, which is in ohms, divided by Z base. But Z base is V base squared over S base. Okay, so which is, what is the V base? What's the voltage here is 20,500. So 20,500 squared divided by S base. What is our S base? The rating in this case, 15,500. 1, 2, 3 kVA. So let's see. So we have 20,500 squared divided by 15, 15500, and then 0, triple zeros, 1, 2, 3 again. So we get 27.11. So that means our Z in per unit will be what I have here, 4.18 over 27.11. So we have 4.18 divided by 27.11. That gives you 0.154. All right, so now the fourth level at this point, rotary capacity, S fault will now be S base over Z total, which will be the same thing as, what's our S base? I'm using this as our S base, 15,500, and then 1, 2, 3, divided by 0.154. Okay, this is 15.5 MVA divided by that. So we can have 15.5 divided 0.154. That will give you 100.65 MVA. 100.65 MVA. Okay, that is that capacity. You can convert that to fault current, so that you would just want to say I short circuit will be S fault over root 3 by voltage, which is 100.65, that's the power 6, divided by root 3 times 20,500 volts, like that. So 100 is, okay, let's say times, divide root 3, divide 20,500. Okay, so you get 2834.6 amps. So it's 2.834 kilo amps. Okay. All right, you get that? Just make sure that your calculator is in order. Now let's look at the next one. The next one is now to get the rotary capacity of this. So how do we get a fourth level at that? We said if I have generator, I have this impedance, and I have this transformer, impedance of the transformer, okay, then just need to get what is happening here. All right. Let's see, what is the impedance of the generator? Did I put that also? Wait, did I? Let's see, did I get a Z total? No, there's a problem somewhere. This is 0 point this, and then Z per unit. We got that at 0.1. Oh, sorry. You know, I forgot to, I put the total and I did not put the total. Okay, it's fine. Let's put the total, sorry. Let's do that. I did not add. Okay, so S fault is S base over Z total. What is Z total? Remember, this is Z for that, so we still have this one. So this will be, what's our S base? 15,500, then 1,000. That's 15.5 million, I mean 0.5 MVA. Now divide by, so I have the first impedance here of the generator, 0.1005, plus the impedance here, 0.154. Okay, let's see. So 0.1005 plus 0.154. Okay, then I need to now take that and divide 15, 5, 2 zeros, and then 3 zeros again. Divide by that will give you 60. That will give you 60.904 MVA. Okay, so that if you want to get the short circuit current, becomes S fault over root 3 by voltage. Okay, and S fault is 60.904. That's the power 6 divided by root 3, and the voltage there is 20,500. So 60 point that, let's say divide by root 3, divide 20,500. Okay, so that gives you 1.715 kiloamps. Okay, so let's now look at this. Let's come here. So I now said if you want to get a reference capacity at this point, now we're going to have, in this case, the impedance of the generator, Z gen, impedance of the cable, Z cable, impedance of the transformer, Z transformer. We said what will be the fault level here. So if we can get this plus this plus this plus this to get our Z total. Okay, but now at least we have the Z of the gen to be 0.1005, and we have the Z of the cable to be 0.154. 154 is our per unit. So we just need to get the Z of the transformer. Now, for us to get that, let's just see what is here. This is Z is the square root of 8 squared plus 1 squared. So 8 squared plus 1 squared. Now the square root of that will give you 8.06. 8.06%, which is 120.08 per unit. That's 1, 2. All right, but remember that this is based on that. Okay, this is based on this, but what are we using as our S base? From all these calculations we've been doing, I'm using this 15,500 kVA as the base value. So you don't just put this in here. You must update it to a common base, okay? So that we have a common base all through. All right, so what we do now, we say, okay, 0.08 in per unit is based on 5,500 kVA. This is based on that, 0.5,500 kVA. So what will it be if you update it to 15,500 kVA? Okay, what will it be? Just to say this divided by that over that, or this times this over this. So that means the Z of that transformer will be the same thing as 15,500 divided by 5,500 times 0.08. Okay, did you get that? So 15,500 divided by 5,500 times 0.08. Okay, let's see. 0.08 times 15,500 divide 55,000. Divide 5,500. Right, I hope that is 5,500, okay? That will give you 0.225. So here is 0.2254. Okay, so that's Z is Z of transformer. Now Z total in per unit will now be this 0.1005 plus 0.154 plus 0.225. 2254. So 0.2254, this is even 2255. Let's say 2255. 2255. So 2255 plus 0.154 plus 0.1005. 0.48. 0.48. That's all. So that S fault, the rotary capacity, our S fault is S base over Z total. All right. Okay, so our S base is that 15,500 kVA, 15,500 kVA divided by Z total 0.48, which is just like 1, 2, 3, 4, 5. 15.5 MVA divided by 0.48. 15.5 divide 0.48. 32.29 MVA. Okay, that is 32.29 MVA. All right, did you get that? I think that's all about that. Then the next, what's the next thing? That's all. You can now calculate the fault current. The fault current, I, short circuit, rotary capacity in kiloamps will now be 32.29 times 10 power 6 over root 3 times, okay, so the voltage, remember, we're not giving voltage here, all right, so you just stop here because there's no voltage. So this is a rupturing capacity in MVA, and this is a rupturing capacity in MVA at this point, and that's the capacity at that point. You can see that the capacity has decreased from 60 at this point to 32 at that point. Why? Because the transformer being there will restrict the fault level. Okay? We reduce the fault level. Did you get that? Well, what time is it now? Yo, it's time to pass, right? Okay. So I think that's all about that question. I think we still have one more question. Let's look at this question. I think after this, okay, we'll have a break. Let's look at this question. have one that you are going to solve. Okay. So let's have a look. So now we have these two transformers. Okay, like that. And this is the ESCOM bus bar. And then we have that, another bus bar here. And then we have this. I think that's all. All right, and so each of the transformer, this is 10 MVA, 10 MVA, and this is 10%, 10 MVA, 10%. And we're given the cable. It's an XLPE cable. Okay, this and this, there are three of them, and each is a 3-core. So we have 3-core, 3-core, 3-core. All right, and the distance is 2 kilometers. And then there's a fault here, and this is 200 meters. And this is PVC or XLPE also, XLPE, and there's 3-core. Okay, and the size is 35 mils. 35 mils, and the size of this is 150 mils each. All right. So the question is to determine the rating of this switchgear. So as I said, if there is a fault in that board, in this board, all right, this will contribute to that fault, and that will contribute to that fault. So in other words, let's look for the fault level at this point. So what you do is you just look for the fault level for one, and this is a 6.6 kV bus bar. Right. So fault level, S base over Z per unit. So that means fault level for one transformer, just one transformer, is just 10 MVA over 0.1, because it's 10%, 0.1, which is 100 MVA. Now, so that fault level for the two transformers, so at the main board will now be 2 times 100, so which is 200 MVA. So if they say we must calculate, determine the rating, now it means we need a board that is rated more than 200 MVA. Okay? So the nearest one is 250. So we can use a 250 MVA. Or if you want to convert to current, you can say I short circuit is S fault over root 3V. So, and S fault is 200 times 10 to the power 6 divided by root 3 times 6,600. Just to see how much it will be in kiloamps. So you have 200 exponent 6 divided by root 3 divided 6600. So you get about 17.5 kiloamps. So you can use a 20 kA board. Something, I think the system is now unstable. Let's see. Okay, sorry guys, the system was all right. Sorry guys, I think there was a little bit of interruption on the network. You can refresh your internet, I mean your browser. So everything is sorted now. Okay, so now there was a little bit of interruption, okay, but it's okay now. All right, so now, so this will be this. That means the circuit breaker size, I mean the switch gear in KA, will be something more than that. Maybe 20 KA, 18 KA, or 25 KA board. All right. Okay, so that's the first thing to determine the main switch gear rating. Number two is to calculate, we're asked to calculate the current flowing along each cable. Calculate how much flowing through here, how much flowing through there, how much flowing through here, and how much flowing through there. All right. So, as I said before, we have many ways of doing it. Right, so we can calculate the fault level. We can calculate, we can use per unit method. We can use ohmic method in ohms. So if I mean per unit, so I can easily get the Z of the two transformers. Okay, let's see like this. So we'll have these two. I will have cable 1, cable 2, cable 3, and then this is cable 4. All right. So just need to look for equivalent impedances like that, so that I'll get this in series. So either I leave it in per unit and use per unit method to solve, or I convert everything to ohms and then use ohmic method to solve. Okay, so let's see which one can we use, which one will be easier. This we'll get this in ohms, and only this in per unit. Or we can leave this in per unit and then get the impedances here in ohms and convert to per unit. Okay, let's see. Let's start with ohms first, so that we can have something that looks like that, and so that here will be 6,600 over root 3, and this is Z of the transformer in ohms, Z of the line, and Z of the line 2, line 1, line 2. All right, so let's start. Now, what will be the Z of the transformer? This transformer impedance is in per unit, so if you parallel them, you have 0.1 parallel 0.1 will give you 0.1 over 2, okay, which is 0.05. Okay. Now, so 0.05, that will be the impedance of this, but that is in per unit. So you can convert that to ohms. So Z of the transformer in ohms is the same thing as Z per unit times Z base. Okay, which is, so that total transformer of 0.05 times Z base is V squared over S. And the voltage is 6.6 kV squared over base 10 MVA. All right. So we have 6.6 squared divided by 10. 4.356. 4.356. This is now in ohms. That's the impedance of that transformer in ohms. Okay? So now once you get that, let's look for impedances of this, that, and that. It's XLPE 150, and then you get a table. You can use this Abade table here. And look for the impedance for 150 square millimeter cable, which we have that to be for 150. We have 0.1847. 0.1847. 0.1847. 0.1847. Let's look at the one for 35 mils. For 35 mils, you have 35 mils, 0.6783. 0.6783. All right. So now, so we have for 150 mils, we have this impedance, and the impedance that is 0.1847 for each one of them, and since they are in parallel, to get equivalent impedance, you divide it by 3. There are 3 of them in parallel, right? So I'm going to divide 0.1847 divide by 3. So I get 0.062. Okay. Then also, this is the impedance of that, 0.6783. And then here is 4.356. Just to make sure this is okay. Okay, let me say that is V squared over S V 6.6 squared. If I put S fault, I got S fault to be 200. Just to make sure it's okay. 6.6 squared divide 200. So 0.2. So there's a problem somewhere. There's a problem somewhere here. Okay. Let's say Z is Z paid by, because this is how much supposed to be, 0.2178. So let me just explain what I did there, because this is it's not correct. Except if I can just do for one. Okay, maybe I think that will be better. Now Z of the transformer for one transformer in ohms, supposed to give you Z per unit by Z base, which is Z per unit is just put 0.1 by this. Let me just see how much you have there. So have 6.6 squared divide 10 times 0.1, 0.4356. Okay, that is for one transformer, and then they are in parallel, so you divide by 2, 0.4356. 356 divided by 2. So divide by 2, you get 0.2178. Okay, which is the same as what you have here. Okay, so here will be 0.2178. So now I have them, all these are in ohms. So that if you want to calculate I short circuit here, which is this, current flowing through here, will now be 6,600 over root 3 divided by all these impedances, 0.2178 plus 0.062 plus 0.6783. Okay, 78 plus 0.062 plus 0.6783. So we have a total now 6,600 divided by that, then divide again by root 3. So I have that to be 3977.15. 3977.15. That is how much current that will flow here. How much that will flow through there. It's 3977.15. Okay. So how much will flow through each of these? Okay, to fit that fault, you divide, because that's what is here is what is here. So I'm going to divide this by 3 to know how much I'll flow through here. All right. So I through the 150 mils cable will be 3977.15 divided by 3. So have that divide 3. I get 1.333 kiloamps. That's how much that will flow through each of these. How much that will be coming from the transformer. I of each transformer will be 3977.15 over 2. Okay. So 3977.15 divide 2, you get 1.99 kA. That's how much that will come from each transformer to feed, and then add up to get that 3.97. Okay. So now the question is for us to know whether the cable will be damaged. Let's see. This is a 35 mils cable, and this is the amount of fault current that will flow through there. For the 35 is just approximately 4 kA. Approximately 4 kA. Let's see whether the cable will damage or not. What do? You go to that Abade table. So you go to this table. Now you look for the short circuit rating of a 35 mils cable. If you go to the nearest, the third to the last column, where you have 1 second short circuit rating, okay, and for 35, there's nothing there. The nearest is 4.6 for 50 mils. So, but you can calculate it. So we're going to calculate. You know what I did before? 35 mils. For 35 mils, let me show you what you can, a table you can use also. 35 for XLPE cable. Let's look at the XLPE. Just want to show you a table that we use. Now look at this table. So for XLPE cable, right, we use for copper, we use 143, that's for multi-core cable. You can see 143 in the third column. So 143 has a value of K. All right, 143. Because I want to use Ka over root T. So 143 times 35 mils divided by the square root of 1. If you are looking at 1 seconds, let's see how much that cable can take. It's 143 times 35. It can handle 5 kiloamps. 5 kiloamps. Okay? Can handle 5 kiloamps, which is okay because the fault current is 4 kiloamps, but that cable can handle 5. Let's see this one. This one, this can handle, this is the fault current flowing is 1.3, and it's XLPE also. So the short circuit rating is 143 times the size of the cable there, which is 150. So it can take a lot. 150, 143 times 150. It can take about 21 kiloamps. So the cable is safe. The cable is safe there, and there's no problem. Okay, if this thing was lower than this, then it means that this cable will be damaged. All right.